Chapter 6 focuses on energy from combustion reactions. And so we will be looking at different fuels and how much energy is released when a specific type of fuel is burnt or combusted. And then we're going to look at electricity and see how it's generated, and then talk about some environmental implications of obtaining and using fossil fuels, and also the benefits and overall sustainability of using alternatives to fossil fuels known as biofuels. Chapter 7 will focus on mainly these alternative forms of energy such as biodiesel and biofuels, solar, wind, so on and so forth. And so there will be a bonus opportunity outlined here for that third chapter exam that will cover chapter 6 and 7. So for now in chapter 6, we're going to focus on the energy from combustion reactions. And so combustion means to burn or generate a fire. So there are 3 requirements in order to perform combustion or to generate a fire. You've got to have a source of heat, some type of ignition source. You've got to have a fuel, and you have to have an oxidizer, which is generally oxygen. When I say oxygen, I mean molecular oxygen, O2, not a single oxygen atom, O. And so when the fuel combines with the oxidizer, and you've got that heat or ignition source acting as a catalyst, and of course the catalyst speeds up the rate of the combustion reaction. So that's the purpose of the heat, the ignition source, is to act as a catalyst. Now, there are many types of fuels, but most of them are hydrocarbons. Hydrocarbons are chemical compounds, and they are molecular compounds. And by their name, they're made up of only hydrogen and carbon atoms. And so carbon, as we know, as we learned Lewis structures this semester, can form 4 single bonds. And so carbon, having 4 valence electrons, it has the ability to form 4 single bonds with other atoms, and therefore be a central atom in the Lewis structure of that compound. And so as far as hydrocarbons are concerned, carbon will form 4 single bonds in these hydrocarbon molecules. And when they are single bonds, and all 4 of them are single bonds, then the specific type of hydrocarbon is called an alkane. And so with the 4 single bonds, each of them being composed of 2 electrons each, that means you have a total of 8 shared electrons. Now, hydrocarbons can also have double and triple bonds. If the hydrocarbon has at least 1 double bond, then it is called an alkene. And I'm going to abbreviate hydrocarbon HC. So an alkene is a hydrocarbon with at least 1 double bond. And an alkyne is a hydrocarbon with at least one triple bond. So we've learned how to draw Lewis structures with all the bonds drawn, whether they're single bonds, double bonds, or triple bonds included in that Lewis structure. So Lewis structures showing all of the bonds are called structural formulas. And then you can represent a molecule using what's called a condensed structural formula that does not show all of the bonds. So this is the hydrocarbon compound. And this hydrocarbon compound contains all single bonds. And so therefore it is an alkane. And if you look at the number of carbons that are in this compound, there are 4. So the particular type of alkane that it is called butane. And so this would be the structural formula. And this would also be another representation of butane's structural formula. You see all the bonds between the carbon and hydrogen and the hydrogens, as well as the carbon to carbon single bonds. And so the next structure is a condensed structural formula for butane. This is also a 4-carbon hydrocarbon, so it is still butane. Now, another way to represent butane and other hydrocarbons and compounds in general is what are called line formulas. They don't show any of the bonds. Whereas a condensed structural formula shows some of the bonds, which are the carbon-carbon bonds. The line formula for butane doesn't show any of the bonds. Each end and each vertex is where a carbon is located. So basically this end, there's a carbon. This vertex, that's a carbon. This other vertex, which I call the point of the V shape, that's a carbon. And then at the other end, there's the 4th carbon. So the ends and the vertices represent carbons. And then it's understood that in order for the octet rule to be met, there's got to be 4 hydrogens attached to each of the carbons on the end and 2 hydrogens attached to each of the carbons in the middle in order for the octet rule to be satisfied. So the line formula only represents the carbons as ends of the lines and the vertices, which I call the tips of the V shape. This is another representation and it's just the molecular formula. It doesn't show any bonds at all. And it's basically just reading the structure. CH3, CH2, CH2, CH3. That's the order in which the groups appear. CH3, CH2, CH2, CH3. So with this molecular formula written here, it just reads the structure from left to right, like you read a book from left to right. And then this representation of the molecular formula, again, you can consider it like a condensed structural formula, again showing the carbon-carbon bonds. So butane is one of many types of hydrocarbons. And the way you name hydrocarbons is based on the number of carbon atoms that hydrocarbon contains. And so here in this table, we have the chemical formulas, the number of carbon atoms in the formula, and the name of the hydrocarbon. So methane has only one carbon, ethane has two carbons, propane three. And then we already looked at butane, its formula is C4H10. And then once we get to 5 carbons, that's when the Greek prefixes come to play. So the Greek prefix for 5 is penta, 6 hexa, 7 hepta, 8 octa. And so once you get to 5 carbons, the names of the alkanes with that ANE ending, you should notice all these alkanes. Those are hydrocarbons only containing single bonds. They all end in the letter ANE. And so once you get to 5 carbons, then the beginning of the name of the hydrocarbon will be based on the Greek prefix. So pentane, 5 carbons, hexane, 6 carbons, 7 is heptane, so on and so forth. And so the 9 is nona and the 10 is deca. So 10 carbons, decane, 9 carbons, nonane. So a hydrocarbon reaction involves the combustion of the fuel. And if the fuel is a hydrocarbon, you'll have your hydrocarbon reacting with the oxidizer, oxygen, O2. And you have your heat source as your catalyst. And then the products will always be carbon dioxide and water. And of course, you also have to make sure that your combustion reaction is balanced. Now, most of the time, fuels are not 100% pure. They usually contain one component that makes up the majority of that fuel, and then there can be other additives to the fuel and other impurities in the fuel. So most fuels, like our gasoline, contains a variety of different hydrocarbons, as well as other additives and other compounds, like sulfur. And so at high temperatures, nitrogen from the atmosphere can also react with oxygen to produce nitrogen oxides, just like sulfur can react with oxygen to produce sulfur dioxide. And so these are also considered combustion reactions. Just like hydrogen is considered a fuel as well, and it combusts to form hydrogen peroxide, H2O2. I'm sorry, H2O, it forms water vapor. And so all of these are considered combustion reactions. The only difference is the fuel is not a hydrocarbon, but those substances react with oxygen just like hydrocarbons do. And so there are some other things that we said are fuels. Hydrocarbons make up the majority of them, but other substances like sugar, glucose. Glucose is found in wood in the form of a polymer known as cellulose, which are just glucose units connected together to form a multiple linkage of glucoses known as cellulose, and it's called a polymer. And so the glucose units in cellulose, when you burn wood, that's what you're combusting is the sugar, the glucose. So when glucose combusts, the products of the reaction are carbon dioxide and water. And then to balance it, we need 6 carbons on each side. We need 12 hydrogens on each side. And therefore, to balance the oxygens, we have 12, 6 times 2, 12, plus 6, 18 on the right. And so we need 18 on the left. So we'll put a 6 here to have 12 plus 6, 18 on the left. The next reaction is the fuel methane, CH4. We've looked at methane a lot already this semester, especially when drawing Lewis structures and figuring out electron and molecular geometries. Again, our products are the same, CO2 and water, and now we just need to balance it. Only 1 carbon on each side is needed. We need 4 hydrogens on each side. And on the right, we have 2 plus 2, 4 oxygens on the right. So we need 4 oxygens on the left. And the last one is propane, C3H8. And again, our products are CO2 and water. And now we need to balance. We've got 3 carbons on the left, so we need 3 on the right. We have 8 hydrogens on the left, so we need 8 on the right. And counting up the number of oxygens on the right, we have 3 times 2, 6, plus 4, 10 on the right. So we need 10 on the left. Now to complete this table, we're given the condensed structural formulas of 3 hydrocarbons. So we need to write the chemical formula, the complete structural formula, and then the name. So this one has 2 carbons. This one has 3, so that's propane. 2 carbon hydrocarbon is ethane. And this is 4 carbons because we have the CH2 in the middle and then in parentheses and then a 2 outside of the parentheses. So that means that's 2 CH2s. And so that would give you 2 carbons plus 3, 4 total carbons. So that's butane. And then we've got 6 plus 4, 10 hydrogens. So you count up the carbons, count up the number of hydrogens, that gives you your chemical formula. And so the structural formula, I've got 2 carbons. Your carbons are always connected together. And then just like in your fashion of doing your Lewis structures, you connect the hydrogens as your outside atoms. Same thing when you've got 3 carbons instead of 2. You connect all the carbons together, and then you put the hydrogens on the outside to satisfy the octet rule, making sure each carbon is surrounded by 8 total electrons or 4 total single bonds. And now your butane with 4 carbons. Again, the outside or the end carbons, the carbons on the end, will have 3 hydrogens attached. The carbons in the middle will have 2 hydrogens attached. So these are all alkanes with all single bonds. And if you look at the formulas are all in the form of C with a subscript N, H with a subscript 2N plus 2, where N is equal to the number of carbons. Now, if you have an alkene, that means you've got 1 or more double bonds in your structure. And so for an alkene, its base formula is going to be CnH2n. Again, N is the number of carbon atoms. And then for an alkyne, which has to have 1 or more triple bonds, its base formula is CnHn. And again, N is equal to the number of carbon atoms. So for the hydrocarbon nonane, it has 9 carbons. Dodecane has 12 carbons. So therefore, if it has 9 carbon atoms and it has the ending ane, meaning it's an alkane, alkenes have the ene ending. Alkynes have the yne ending. And then alkanes have the ane ending. So these are hydrocarbons, which are alkanes because they have the ane ending. So they have all single bonds. So their base formula is CnH2n plus 2. So if nonane has 9 carbons, N is the number of carbons. So if it has 9, then that's C, and then N is 9, then H, 2 times 9 plus 2, which is C, 9, H, 20. So that's the formula for nonane. For dodecane, with 12 carbons, that's C, 12, H, 2 times 12 plus 2. That gives you C, 12, H, 26. And that brings us to the end of our short lecture on combustion reactions.